Okay, so we have here video solutions for homework 3.5 through 3.7. So here we are asked to show that these two curves are orthogonal trajectories of each other. And we have to find the points of intersection. I use substitution, x squared plus y squared, they're both the same on the left-hand side, so then ax must equal by. I solved for x, and I went back to the second equation and plug it in. So b over ay, everything squared, and then plus y squared equals by. I squared, and I moved by to the other side. And set it equal to 0. So I squared this, and since both have y squared, b squared over a squared, y squared, I factor out y squared, so I have b squared over a squared plus 1. And I factor out y, and I got a squared here, a squared plus b squared over a squared times y minus b. So there are two possible solutions when y is 0, by zero product principle, y is 0, or this is 0, which when we move b and divide by this, we get a squared b over a squared plus b squared. I have to go back in and replace y to get x. So b over a times y. I simplify a, and I get ab squared over a squared plus b squared, and this is my x. So there are basically two possibilities: p of intersection, 2 points of intersection, p with 0, 0, when y is 0, x is 0, and q with this x, ab squared over a squared plus b squared, and a squared b over a squared plus b squared as the y value. Now I find the derivatives, the dy over dx for the first curve, number 1, and dy over dx for the second curve. So I have 2x plus 2y dy over dx equals a. 2x plus 2y dy over dx for curve 1 equals a. And I subtract 2x and I divide it by 2y. So a minus 2x over 2y is the first derivative. For the second derivative, I have 2x plus 2y dy over dx plus b dy over dx. 2x plus 2y dy over dx for curve 2. B equals b dy over dx for curve 2. I move these terms to one side, and I divide by 2x. Or you move this one here and this one here, it doesn't matter. The answer would be the same. So dy over dx for curve 2 is negative 2x over 2y minus b. Now I evaluate the derivatives for each point of intersection and make sure that, like in this situation, this is a vertical tangent, this is a horizontal tangent. A horizontal tangent and a vertical tangent will definitely be perpendicular. So for point A, I conclude they are orthogonal trajectories at this point of intersection. But now I have to check the other point of intersection. So I plug in dy over dx, I plug in this x and this y, and realize after all simplifications, I get this. And I find dy over dx for q for the second curve. And after all simplifications, I got this. And we know that two lines are perpendicular if the product of the two slopes equals -1. So I multiply this by the first slope, this right here, a squared minus b squared over 2ab. And it turns out that I got the product of -1. Therefore, orthogonal trajectories at q as well. So curves are orthogonal trajectories of each other. I tested at all points of intersection. Here we're asked to find the derivative, so 1 over natural log, 1 over sine squared, it's because the derivative is 1 over sine squared x. Now I have to differentiate sine squared x, which is 2 sine x, subtract 1 from the power, times the inner function prime, which is cosine. I simplify a sine, and I have 2 cosine over sine, which is 2 cotangent. Here I have, to differentiate this function, it's 1 over 2 the square root times the inner function prime. You may say, well, how come that I chose this? It's the same function. 1 or 2, it doesn't make any difference. Because it was asking us to determine the domain of this function as well. So two conditions here. Natural log to exist, x has to be strictly greater than 0. But on top of that, we have a square root. So therefore, 2 plus natural log x must be a number greater than 0. When I move to the other side, I realize that natural log has to be greater than -2. First, I have to solve the equation natural log x equals -2. And I change this into e raised to this power equals x. So x becomes e to negative 2, or 1 over e squared. So what happens here is this. This is the graph of natural log x. This is the graph of y equals negative 2. They intersect at this point, and we determine the x value algebraically, 1 over e squared. So I need to determine x such that natural log x is above this line. It will always be above this line between 1 over e squared to infinity. So the domain of this function is 1 over e squared to infinity. In this case, you just solve a logarithmic inequality. And the derivative is the same. Okay, now here we cannot use any rule, any differentiation rule. We have to apply natural log to both sides. And when we apply natural log to this side, cosine becomes a factor in front. And now we have a product, and we have to use the product rule. When I differentiate implicitly natural log y, I get 1 over y dy over dx. When I differentiate cosine, I get negative sign, and I copy the second function plus the first function times. Now, careful, I need to differentiate natural log, so it's 1 over natural log, but now the inner function prime is 1 over x. I multiply both sides by y in the form of the given function, natural log x raised to cosine x. I copy this term, and I copy this term condensed. Cosine at the top, x in the front, x natural log x. Next problem, g prime, 1 over natural log, 1 over arctangent t to the fourth, multiplied by arctangent prime, which is 1 over 1 plus the argument squared. But t to the fourth squared is t to the eighth, times the further inner, or the last function, the innermost function, t to the fourth prime, which is 4t to the third, and I condensed it here. Finally, this last problem was asking us to find the maximum, of the distance and where the maximum occurs. So we find the derivative. We set it equal to 0. We determine the time needed for a maximum for function s of t. We plugged it back in the function, we get 100 feet. But the question is this a maximum? Without explaining why this is a maximum and without studying the sign of the derivative, we cannot get full credit. So s prime, s 100, 2.50 for the derivative. And when you study the sign, when you plug in 0 here, you see it's positive. When you plug in 10 here, you're going to see it's negative. So obviously, this is the situation for a maximum, guaranteed, for sure. Then we are asked to determine the velocity going up and going down when the distance is 96 or the height is 96. Oh, this was the height. Yeah, not the distance, the height. So we set equal the distance function to 96. I need to solve and find what is the time needed for the ball or particle to reach 96 feet. So I simplify by 16. I got this, t squared minus 5t plus 6. I factored, and I got 2 and 3. Going up, obviously, because it's 2 seconds, and going down because it's 3 seconds. Why is 3 seconds? Because after the maximum is reached at 2.5 seconds. So obviously at 3 definitely is going down. Also, that is expressed by the fact that this is a positive slope. It's going down, direction up, increasing. And this is a negative, going down, decreasing. So the rate of change, the negative rate of change shows direction in this case. Thank you.